This is the second lecture of week number 10, and in this lecture we will go through two examples related to the air conditioning part of the course. One example will relate to cyclometry and the other will be related to the terminal reheat system that we had studied when we were looking at various air conditioning systems. So let's proceed to the first problem, and I will just show you the problem statement, and then once we have gone through the problem statement we will decide what it relates to, and then we will go through the solution procedure. So we have the problem statement in front of us, in which you are told that moist air enters a room at a certain dry bulb temperature. Then the other piece of information is the exit dry bulb and wet bulb temperatures of moist air when it leaves the room, and during this process there is a sensible heat gain at a rate of 9 kilowatts, and in addition there is also a moisture gain of 0.0015 kilograms per second, and we are told that this moisture gain can be considered equivalent to saturated vapor being introduced into the air stream at 30 degrees C, and we are asked to find out the wet bulb temperature and volume flow rate of the air when it enters the room. If you try to analyze this problem, there are two things happening to the air. It has been sensibly heated and there is addition of moisture to that air stream. So this is a process which is equivalent to the heating and humidification process that we had studied, and we have the requisite mathematical equations for that process, and we also know how to represent it on the cyclometric diagram, and that is the first thing that we will do. We will represent it on the cyclometric diagram, that is a sketch, and then we will proceed with the solution, and I will also go to the psychrometric chart, the actual psychrometric chart, to verify the various values that we will find out in the solution. So we start with the solution, and we can see that there is a sketch of the process which shows from 1 to 2 there is sensible heating, and from 2 to 3 there is addition of moisture, and the process, the net process of heating and humidification from state 1 to 3 can be shown. And for this process from state 1 to 3, which includes both sensible heating from 1 to 2 and addition of moisture from 2 to 3, that is humidification, we have the result from our previous analysis that delta H by delta W is equal to Q dot by M dot W plus HW. Q dot is the rate at which we provide the sensible heating, M dot W is the rate at which moisture is added to the air stream, and HW is the enthalpy of the water which is added to the air stream, and we are told that this moisture that is added to the air stream can be considered to be saturated vapor at 30 degrees C. So we can obtain the value of HW, which is equal to Hg at 30 degrees C, and that is obtained from table A1. Substitute the values, because Q dot is given to us, that was 9 kilowatts. The mass flow rate of water, that is also given to us, that was 0.0015 kilograms per second. So those values can be inserted into this expression, and that comes out to be 8556.4 kilojoules per kilogram. And we will make use of this value on the psychrometric chart, the actual psychrometric chart, and recall that this value delta H by delta W in the actual psychrometric chart has units of kilojoules per gram. So we have to divide it by 1000, and that is now the value that we will make use of when we move to the psychrometric chart. So the first thing that we can now do is, we know that this value delta H by delta W is shown on the protractor, that is the scale on the outer side corresponds to delta H by delta W, and we can establish this reference line on the protractor, and the same direction will also be there in when we move to the psychrometric chart. So we know that we can locate state 3 because we know the exit conditions of the air, that is the dry bulb and wet bulb temperatures are known, so we can locate state 3 on the psychrometric chart. But state 1 right now was not known. All we knew was the dry bulb temperature of 15 degrees C, that is T1 was 15, but we did not know, if I want to just indicate that over here, that let's say if this is 15 degrees C over here, we did not know at which point on this line state 1 lies, and that is what we need to establish. And to do that, we need the process line 1, 2 with the correct direction, and that is obtained from the protractor. So once we have got the line drawn on the protractor, we will draw a line parallel to this line from state 3, and it will intersect this line of constant T1 at some point, and that is the state that we are interested in at the inlet, that is state 1. So once these two lines these two lines intersect, state 1 will be located on the psychrometric chart, and at state 1 then we can read off the wet bulb temperature from the corresponding wet bulb temperature lines, and that value I've shown to be 14.1 degrees C. So that answers the first part of the question. The second is, we need to find out the volume flow rate of the air at the inlet, and to do that we will need the mass flow rate of the air, that is the kilogram dry air per second value. To do that, we can perform an energy balance on the air when we move from state 1 to 3. And what is happening, we can easily look at this equation over here, which describes what happens to the air when it enters the room and when it leaves the room. When it enters the room, it has an energy content of m dot a h1. Because it is sensibly heated at a rate q dot, so we add that to the energy at state 1. In addition, when you add water or moisture, it will also carry energy with it, and that will be equal to m dot w hw, and that together, all these three terms, when they are summed up, that will be the energy content of the air when it leaves the room, that is at state 3. So you will have m dot a h3, and what you can do, you can just take m dot a h1 onto the other side, take m dot a common, you will get m dot a into h3 minus h1, and on the other side of the equation we will have q dot plus m dot w hw, and then we can easily find out the mass flow rate of dry air per second, that is kilogram dry air per second, by this equation. And in this equation, q dot, again as I mentioned earlier, it is given to us. Similarly, m dot w is also given to us. H dot hw we obtained from the table, that is table A1. And what we need are values of h3 and h1. Because we have located states 3 and 1, these values of the specific enthalpy can be found out from the psychrometric chart, which I have shown over here to be 54 and 39.5, giving us the mass flow rate as 0.885 kilogram dry air per second. Another thing that we will need will be the specific volume, and again from the psychrometric chart, because we have already located state 1, the specific volume is also obtained as 0.828 meter cube per kilogram dry air. And then finally, the volume flow rate at the inlet to the room will be the product of the specific volume and the mass flow rate, and that comes out to be 0.733 meter cube per second. what we can now do is to go to the actual psychrometric chart and try to verify the values that I've shown over here. There might be a slight difference because these values were calculated by using the psychrometric chart on paper with instruments, so there might be a slight difference when we do it on the computer. However, they should be fairly close to together. So I will go to the psychrometric chart and reconstruct the process and look at the resulting values. Okay, now we start with state 3, which we can easily locate because we know the dry bulb temperature is 25 degrees C and the wet bulb temperature is 19 degrees C. And you can see that I have already marked off this state on the psychrometric chart corresponding to a dry bulb temperature that's provided to us and the wet bulb temperature that's given to us. And we can also draw a line on which state 1 will lie. We know that it has a dry bulb temperature of 15 degrees C, and we have 15 degrees C over here, and I will just draw a vertical line over here to show that this is the line on which state 1 will lie. Where we do not know that yet. And as you can recall from the solution, what we had done, we had found out the value of delta H by delta W, which was 8.5564, approximately 8.6, and we go to the protector and look at the value of 8.6 on the outer scale. So we have got, this is 5, then we have 6, 7, then we have 8, and almost in the center of 8 and 9 we will have 8.66. So that is the direction of the process, and what I need to do is to just again draw a line which is parallel to this line from state 3, and wherever it intersects this constant dry bulb temperature line of 15 degrees C, that will be the location of state 1. And you can see that we have got the intersection point over here, and I will again mark that point. Slightly off. Okay, so I've got those 2 points, and I'll also identify them as such. This is state 3, so that is 3 over here, and the other is state 1 over here. Okay. So we've got the 2 states, one at the inlet, the other is at the outlet. Once we had done that, the first thing we wanted to find out was the wet bulb temperature at state 1, and again you have to draw a constant wet bulb temperature line which passes through state 1, and you can see those broken lines over here or dotted lines over here. These are the constant wet bulb temperature lines, and I need to just take one of these and you can see this is 15. So this line that we are looking at over here is 14 degrees C, and we are just around that mark. So the state point is just above, slightly above the 14 degree C dry bulb temperature line, and I had obtained the value as 14.1 degree C. So this line that I have shown is 14, and if I move it slightly upwards, it will be around 14.1 degree C. Okay. So I can slightly try to shift it upwards, and that will be the wet bulb temperature at state 1. And then we had performed the energy balance to find out the volume flow rate entering the room, and to do that we required the values of the enthalpies at states 3 and 1, and also the specific volume at state 1. And I will move on to those values of enthalpies, then I will come to the specific volume. So just to again make the drawing a little less cluttered, I will remove this information about the wet bulb temperature, which is already there in your recording. And then I will just focus on the enthalpy. You can see that this value over here is above 50, and again we can draw a constant enthalpy line which will pass through this state point and read off the value from the scale. So I will just take it over here, and you can see the value is, if this is 50, 51, 2, 3, 54 kilojoule per kilogram dry air. And again I will just write this numerical value. The units we already have on the scale, so I'm not writing those down. The other line will be for state point 1, and I will take that as well over here. And you can see this is close to what I have written as 39.5 kilojoule per kilogram dry air. So these values are corresponding with those that I had earlier shown you in the solution. And finally we just need the specific volume, and the specific volume, constant specific volume lines you can see are over here. This is 0.82, this is 0.83, and this is 0.84, and the value that we have in the solution is 0.828. And again let's just confirm that last value, and to do that I will just again draw a constant specific volume line. This line is, then we will look at its value when I move it to the state point at state 1. So you can see that this is just slightly, this is 0.82, the value is quite close to 0.83, so it's around 0.828 or 0.8275 meter cube per kilogram dry air, and I have used a value of 0.828 meter cube per kilogram dry air. And again, just to finish it off, I will write down that value, not 0.828, and the units again you can see are cubic meter per kilogram dry air. And that completes the solution. So all that we required in this problem was to first read the problem and try to identify what it related to. It was actually a process, and the process that was applicable was of heating and humidification. We will now move on to the second example and see what it relates to and how it can be solved. So we are told that it's a winter air conditioning system. That means we will be working with the heating cycle, and the only heating cycle that we have studied is the basic heating cycle, and we will of course sketch that cycle on the psychrometric diagram, and then we will have to move to the psychrometric chart to find out various values that are required to solve this problem. So if you look at it, the space is being supplied with air at 2 kilograms per second, and this is 2 kilograms dry air per second. So if you are given the mass flow rate of air, it is kilogram dry air per second, and sometimes it is just written as kilograms per second. We have a heater and humidifier. For the purpose of heating and humidification, we are told the heat loss from the space is 28 kilowatts, and that means, because we are given a sensible heat factor of 0.6, that means there is going to be both latent and sensible components of the total heat loss, and that you can work out by using the sensible heat factor if you are asked to do that. We are told that the space is being maintained under certain conditions, that is the dry bulb and wet bulb temperatures are given, and we are also told the proportions of the recirculated air and the outside air which are mixed to provide us with the desired air condition when it is supplied to the space. We are also given the outdoor air conditions, dry bulb temperature and relative humidity are given, and we are told that humidification is done by spraying saturated steam at 120 degrees C. So the first thing that we will do is sketch it on the psychrometric diagram. That is just a sketch. We have to calculate the sensible and latent heat loads, the rate of heat input by the heater, and the rate of moisture addition by the humidifier. And let's move on to the solution. The first thing that we have to again go back to is the representation of the cycle. So you can see that the cycle is the familiar cycle. We have the outside air shown by the symbol O, recirculated or the room air condition by the symbol R, and then they are combined together or mixed together to give us state M, and that is the state M which will first be sensibly heated. That is from M to this point A, that is shown the heating, sensible heating, and the rate of sensible heating in this solution is shown by Q dot H. And from A to S, there is humidification by spraying steam at 120 degrees C, and then we achieve the desired supply state, that is state S. And remember that in the basic heating cycle, the supply state will have a higher humidity ratio and a higher dry bulb temperature than the humidity ratio and dry bulb temperature that are required in the conditioned space, and that is to balance the heat loss, and that heat loss will have or can have both sensible and latent components. So we can again look at the data, and you can see that state R can be located because we know the dry bulb and the wet bulb temperatures. We can also locate the state O because we know the dry bulb temperature and relative humidity. So states R and O can be straight away marked on the psychrometric chart. And as I said earlier, the mass flow rates of the recirculated air and the outside air as a proportion of the supply air are also given to us. Remember that the mass flow rate m dot as is the same as the mass flow rate at state M, because what you do, you combine the recirculated air with the outside air, and then that whatever that mass flow rate is there as a result will first be sensibly heated, then humidified, and then it will be supplied to the conditioned space. And then this is the mass flow rate of dry air, so it's kilogram dry air per second. So even when you are spraying steam, that value does not change, it remains the same. We were also asked to find out the sensible and latent components of the heat loss from the conditioned space. Okay. You can see that because we were able to locate states O and R, I have found out or given you the values of the enthalpies at states O and R. Then we move on to the sensible heat factor, and we know that the sensible heat factor is the ratio of the sensible heat loss or heat gain divided by the total heat loss or heat gain. We are given the total heat loss as 28 kilowatts and the sensible heat factor is 0.6. So the sensible heat loss from the space is 16.8 kilowatts as shown over here. Then the latent heat loss again can be easily found out, because we know that the total heat loss is the sum of the latent and sensible heat loss values, and that gives us the latent heat loss, which comes out to be 11.2 kilowatts, and the sum of the two must be equal to 28 kilowatts. So 11.2 plus 16.8 will give you 28 kilowatts. The next thing is to move on to the other as yet unknown states of the cycle. We have got two states, we need at least M and S. Then we can draw the complete cycle, and that will then allow us to obtain further results. So to locate state S, what we can do, we can start first by looking at the energy balance for the process RS, and during this process RS, what we are showing is that there is energy loss from the conditioned space, and that total value is Q dot, which is given to us 28 kilowatts. The mass flow rate of dry air at the supply condition, that is also given to us 2 kilograms dry air per second, and the enthalpy difference between the two states will be HS minus HR. HR we have also found out earlier because we located state R, and then we can easily find out the enthalpy HS, which comes out to be 56 kilojoules per kilogram dry air. Once we have got the specific enthalpy at state S, we need some other piece of information that will help us locate state S on the psychrometric chart. And if you look at the equation, the data given to us, the sensible heat factor can quite conveniently be used for that purpose. What we can do, we can go again to the protector, draw a reference line with a sensible heat factor of 0.6 on the protector, and then we will draw a line on the psychrometric chart which is parallel to this line, and where it will intersect the line of constant enthalpy of 56 kilojoules per kilogram dry air, that will give us state S. And just on the same figure, I'll try to just give you the basic idea, and then when you work with the actual psychrometric chart, you should be able to get the desired values. So I'll just move it a little bit over here. Let's say we have the protector on the psychrometric diagram somewhere over here where the cursor is, and I need to draw a process line with a slope of 0.6. So if I draw a process line of 0.6 somewhere over here, so that is on the protector, and remember we have a constant enthalpy line for state S. So the first thing, this was corresponding to a value of 56 kilojoules per kilogram dry air, and what we didn't know that where on this line state S will lie. So what I have to do is draw that line from R. I will draw a line which is parallel to the line that I have marked on the psychrometric on the protector, and the intersection of these two lines will give us state S, and that is how state S will be obtained on the actual psychrometric chart. So I can again remove these lines and go back to the solution that I was going through. Once we have located state S, we can find out the humidity ratio, which is 10.5 grams per kilogram dry air. This is the value that you read from the psychrometric chart. So what we are now left with is this is state M, and if required that state A, and we can move on to state M, because we know that it is obtained by applying the results of adiabatic mixing of two air streams, and those two air streams are at states R and O. So let's move forward and apply those results. So you can see that the energy at state R plus the energy at state O is equal to the energy at state M. So this is just a energy balance, and we know that the mass flow rate of dry air at state M is the same as the mass flow rate of dry air at the supply state, which was given to us. The mass flow rates of recirculated air and the outside air, they were also given to us as a proportion of the supply state. So those values have been inserted over here, which will give us the enthalpy at state M. And once we have the enthalpy at state M will be located, because we know it will lie on the straight line connecting states O and R. So you draw a line which connects states O and R, and draw a line of constant specific enthalpy with a value of 28.6 kilojoules per kilogram dry air. It will give us state M. At that state, the humidity ratio comes out to be 5.2 grams per kilogram dry air. And as I said, the only remaining state is now state A, and because from A to S, that is a humidification process, and again we can use the results that we had looked at earlier when we were studying various psychrometric processes. For the humidification process, delta H by delta W is equal to HW, and HW will be equal to Hg at 120 degrees C, and this value we get from the table, that is table A1, and you can see that the value has been obtained as 2706 kilojoules per kilogram. And because we now need to move to the protector on the psychrometric chart, we have to convert it into kilojoules per gram. We get the desired value of 2.706 kilojoules per gram. So this should be in kilojoules per gram. Let me just correct it over here. And that is the value that we will mark off on the protector. So you go back to the protector, and this time use the outer scale with a corresponding value of 2.7. Draw the line over there. Then you will have to draw a line parallel to that line from state point S, and this will intersect the constant humidity ratio line drawn from state M, and that intersection of these two lines will give us state A, because remember from M to A we have sensible heating, During that process, the humidity ratio will remain the same. And from S or A to S, we will have humidification. So draw a constant humidity ratio line from M, draw a line right up to the end of the scale, and then when you draw the line parallel to the line that you get from the protector, corresponding to a delta H by delta W value of 2.7, the intersection of the two lines will give you state M, will give you state A, and at state A the humidity, then specific enthalpy comes out to be around 41.6 kilojoules per kilogram dry air. And then we need to find out the amount of sensible heating, and that's a simple energy balance. The mass flow rate into the change in enthalpy. The enthalpy changes from M to A, so HA will be higher, HA minus HM into M dot AM, all the values we have, and that gives us the sensible heating rate of 26 kilowatts. And the amount of moisture that is added, again we use the basic result that M dot W is M dot A into delta W, and the delta W values will be between states S and M. You can say states S and A, or states S and M. They are the same because the humidity ratio at A is the same as the humidity ratio at state M, and we get a mass flow rate of saturated steam to be 0.0106 kilograms per second. And I leave it to you to pick up the psychrometric chart and again verify these results that I have given to you. And again, just to again repeat the point that I mentioned earlier, your values might be slightly different than the values that I have got, so we allow for a little variation in the values when you read those values from the chart, but they should be fairly close. We will continue with another example in the next class.